Everything you have ever seen is just a tiny fraction of reality. All the stars, galaxies, and swirling nebulae in the night sky amount to less than 5% of the cosmos. The rest is made of two profound and invisible mysteries, dark matter and dark energy. These forces hold the universe together while simultaneously tearing it apart, and they define everything from the fate of galaxies to the ultimate destiny of all existence. By the end of this journey, you will have explored 30 of their deepest secrets, from ghostly particles to a repulsive force woven into empty space itself. We will see how the gravity of unseen matter bends light into cosmic mirages, and why the universe's expansion is accelerating against all odds. What does it mean that 95% of reality is completely unknown to us? The story of our cosmic blindness begins not in deep space, but with a brilliant and often irascible astronomer named Fritz Zwicky. In the 1930s, Zwicky turned his telescope toward the Coma Cluster, a dense swarm of galaxies millions of light years away. He was studying how these galaxies moved, using their velocities to weigh the entire cluster. The result was a profound shock. The galaxies were orbiting each other far too quickly. According to the laws of gravity, the cluster should have flown apart long ago, its member galaxies scattered into the void. The only possible explanation was that the cluster contained a tremendous amount of unseen mass, a hidden gravitational glue holding everything together. Zwicky called this missing stuff dunkel materie, dark matter. For decades, many in the scientific community dismissed his idea as an oddity, a miscalculation perhaps. That changed forever in the 1970s, thanks to the meticulous work of astronomer Vera Rubin. She wasn't looking at clusters, but at individual spiral galaxies, charting how fast stars orbit around their centers. Everyone expected stars farther from the galactic core to move slower, just as Pluto orbits our Sun more sluggishly than Mercury, but Rubin's data painted a different picture entirely. Stars at the very edges of galaxies were whipping around just as fast as those near the center. It was as if the entire galaxy was embedded in a vast, invisible sphere of matter, its gravity keeping the outer stars from flying off into space. Her rotation curves became the definitive, undeniable proof. Something was there, exerting a colossal gravitational pull, yet emitting no light whatsoever. This is the missing mass problem in its starkest form. All the stars, gas, and dust we can see with every telescope across every wavelength account for only a tiny fraction of the gravity we actually measure. Dark matter outweighs the ordinary matter that makes up our world by a factor of about 5 to 1. For every galaxy we admire, there is an immense, silent halo of this unknown substance, a ghostly scaffold upon which the visible universe is built. The discovery of dark matter's gravitational pull was just the beginning of a much deeper puzzle. We know it's there, we can map its immense influence, but the fundamental question remains: what is it actually made of? This is the second great mystery, and it has launched one of the most ambitious detective hunts in the history of science. The prime suspect for decades has been a theoretical particle known as a WIMP, which stands for Weakly Interacting Massive Particle. The name itself is a perfect description. These hypothetical particles would have mass, hence their gravitational pull, but they would interact with ordinary matter only through the weak nuclear force and gravity, making them virtually ghostly and invisible. Their appeal is deeply elegant. Theories like supersymmetry, which propose a partner particle for every known particle in the Standard Model, naturally predict a stable, neutral particle with just the right properties to be dark matter. It was a beautiful convergence of particle physics and cosmology, a solution that seemed too perfect to ignore. This belief led to a global effort to catch a WIMP in the act. Laboratories were built deep underground, in abandoned mines and beneath mountains, to shield them from cosmic rays. The idea is to fill a vast chamber with an ultra-pure liquid, like xenon, and wait. If a WIMP, drifting through the Earth, were to ever bump into the nucleus of one of these atoms, it would create a tiny flash of light or a jolt of charge. Scientists have waited for years in profound silence, listening for that singular, universe-revealing ping. So far, they have heard nothing. The profound quiet in those detectors has forced physicists to broaden the search. Another compelling candidate is the action. Imagine a particle so incredibly light that trillions of them could pass through your fingertip every second without you ever noticing. Actions were first proposed to solve an unrelated fine-tuning problem in the strong nuclear force, but they also possess the right traits to be dark matter. Instead of hunting for a rare, heavy collision, experiments for actions look for a subtle conversion. In the presence of a powerful magnetic field, an action might very rarely transform into a faint microwave photon, a whisper of radio waves that could be detected with exquisitely sensitive antennas. The search feels less like trying to catch a bullet and more like trying to hear a single snowflake land in a silent forest. Beyond WIMP and actions, the suspect list includes other exotic possibilities. Sterile neutrinos, heavier cousins to the known, nearly massless neutrinos, could be buzzing through the cosmos. There is even the dramatic possibility that some dark matter is made of primordial black holes, not the kind formed from dying stars, but tiny ones forged in the seething chaos of the Big Bang itself. Each candidate points to a radically different vision of the underlying physics of our universe. The ongoing experimental hunt, from deep underground to laboratory tables, is a testament to our determination. We are trying to identify a substance that shapes the cosmos by feeling for its shadow in the dark. The search for dark matter's identity often feels indirect, like studying a ghost by the objects it moves. But in 2006, astronomers witnessed an event that provided something much closer to a cosmic crime scene photograph. They call it the Bullet Cluster. Nearly 4 billion light-years away, two enormous galaxy clusters, each containing hundreds of galaxies, slammed into one another in a collision of almost unimaginable scale. This was not a slow merging, but a violent, high-speed crash. For scientists, it became a perfect natural laboratory, a chance to see how different components of the universe behave under extreme conditions. They pointed a suite of telescopes at the aftermath, and the resulting image told a startling story in multiple layers of light. The Chandra X-ray Observatory saw the hot gas that fills the space between galaxies, the majority of the normal, baryonic matter in the clusters. This superheated plasma, visible only in X-rays, behaved exactly as you would expect in a colossal collision. It was like two clouds of smoke hitting each other, the gas particles interacting, slowing down, and getting stuck in the messy middle of the impact. But when astronomers mapped the cluster's total mass using a technique called gravitational lensing, they saw something completely different. This method doesn't rely on light emitted by the cluster, but on how its gravity bends and distorts the light from galaxies far behind it, acting as a cosmic scale. The map of where the mass actually was did not line up with the glowing X-ray gas. Instead, the bulk of the mass, the true gravitational anchors of the clusters, had sailed right through the collision site. Two huge clumps of mass were now located on either side of the central pile-up, having passed through each other almost without a whisper. This is the smoking gun. The hot gas, the normal matter we understand, got caught in the traffic jam. The dark matter, which does not interact with the electromagnetic force, felt no friction, no drag, and simply kept going. It proved that dark matter is not just hidden ordinary matter like cold gas or failed stars. It is something fundamentally different, a substance that feels gravity but is essentially collisionless, ghostly and transparent to itself and to everything else. The bullet cluster gave us a direct, observational separation of dark matter from the ordinary stuff of stars and planets. It showed us that the universe is truly dual in nature, with a shadow framework that moves independently through the visible world we call home. That ghostly, collisionless nature of dark matter does more than just hold galaxies together. It built the entire large-scale architecture of the universe. Think of the cosmos not as a random scattering of stars, but as a single, breathtaking structure, a cosmic web. This web has dense nodes where thousands of galaxies swarm in massive clusters. Those nodes are connected by long, thin filaments of matter, stretching across hundreds of millions of light years, and between these threads lie the vast, empty voids, deserts of space nearly devoid of galaxies. This is the grand design of our universe, and dark matter is its master architect. We know this because of supercomputer simulations that trace the history of everything. Scientists start with the near-uniform soup of matter and energy in the very early universe, as seen in the cosmic microwave background. They program in the laws of physics with one crucial ingredient, a dominant amount of cold, slow-moving dark matter that feels only gravity. Then they press play and let the simulation run for 13.8 billion years. What unfolds is a story of gravitational collapse on a cosmic scale. Tiny quantum fluctuations from the Big Bang, magnified by inflation, serve as the seeds. Dark matter, responding only to gravity, begins to clump around these slightly denser spots. Over eons, it draws more and more material inward, forming an intricate network, a skeleton of dark matter filaments. The ordinary matter, the atoms that make up stars and planets and us, is just along for the ride. This normal matter feels the same gravitational pull, so it follows the dark matter's lead, streaming along the filaments like water flowing into riverbeds. Where filaments intersect at the knots of the web, dark matter forms immense spherical halos. It is into these deep gravitational wells that hydrogen and helium gas cascades, cools, and finally ignites into the first stars, birthing the galaxies we see today. The stunning visualizations from these simulations, like the Millennium Run or Illustris TNG, are not artistic guesses, they are precise mathematical predictions. They generate universes that look, in their large-scale structure, statistically identical to the maps we create by painstakingly surveying millions of real galaxies across the sky. The agreement is uncanny. It means we are not just seeing patterns, we are understanding the process. Every galaxy cluster, every sprawling filament of galaxies observed by our telescopes, exists because an invisible framework of dark matter laid down the blueprint first. The luminous universe is merely the decoration on a hidden scaffold of staggering proportions, but how can we possibly know the exact recipe of the cosmos, the precise percentages of dark matter and dark energy? The answer comes from the oldest light in existence. When you turn on an old analog television and see the static snow between channels, roughly 1% of that flickering noise is the cosmic microwave background radiation. This is the remnant glow from the hot, dense infancy of the universe, now cooled to a faint microwave whisper after traveling for 13.8 billion years. It is the ultimate baby picture of everything, and etched into its subtle patterns is the complete blueprint for what the universe would become. Space telescopes like Planck have mapped this afterglow with breathtaking precision, measuring its temperature down to millionths of a degree. The map is not perfectly smooth, it is a modeled tapestry of slightly warmer and slightly cooler patches. These tiny fluctuations are not random, they are frozen sound waves, the echoes of the universe's first cries. In the searing heat of the first few 100,000 years, the cosmos was a plasma soup of particles and light, constantly pushing and pulling against the relentless grip of gravity. Normal matter, made of protons and electrons, was tightly coupled to light, creating a thick, opaque fog, but dark matter, unaffected by light's pressure, was already quietly clumping under its own gravity, creating the gravitational seeds for everything to come. The ordinary matter and light, trapped together, sloshed in and out of these dark matter wells, creating vast, rhythmic pressure waves that traveled through the primordial soup. When the universe finally cooled enough for atoms to form, in a moment called recombination, the fog cleared, the light was suddenly set free, and those pressure waves were frozen in place, imprinted as minute temperature differences on the sky. The precise size and distribution of these hot and cold spots tell a detailed story. They reveal how fast those sound waves were traveling, which depends on the density and composition of the early soup. By analyzing these patterns like a cosmic barcode, scientists can deduce the exact proportions of the ingredients. The Planck data gives us the definitive recipe. A mere 4.9% of the universe is the ordinary atoms that build stars, planets, and us. Dark matter, the gravitational scaffolding, makes up 26.8%. And the dominant force, driving the accelerating expansion, is dark energy, accounting for a staggering 68.3%. This single snapshot from the dawn of time tells us that the universe we see is just the glittering froth on a deep, dark sea of unknowns. But how do we see a scaffold that casts no shadow? We use the universe's own trick, a phenomenon predicted by Einstein where gravity bends the very fabric of reality. It is called gravitational lensing, and it turns dark matter into a cosmic magnifying glass. According to general relativity, a massive object warps the space and time around it. Light traveling along this curved geometry does not follow a straight line. Instead, its path bends just as a marble would roll along a curved sheet. When the alignment is just right, the gravity of a foreground galaxy cluster can distort and magnify the light from galaxies billions of light years behind it, creating nature's most powerful telescope. There are two ways this reveals the unseen. The first is strong gravitational lensing, which creates breathtaking cosmic mirages. When the background galaxy is directly behind a massive cluster, its light can be bent into perfect circles of light known as Einstein rings. More often, the alignment produces multiple, stretched and distorted images of the same galaxy, like reflections in a funhouse mirror. These dramatic arcs and duplicates are a direct signature of immense mass, a signpost pointing to the vast, invisible halo of dark matter enveloping the cluster. But most of the dark matter in the universe does not create such perfect alignments. To map its broader, subtler distribution, astronomers use weak gravitational lensing. Imagine looking at a field of distant, faint galaxies. Each one is inherently a slightly oval shape, but if a vast filament of dark matter lies between us and those galaxies, its collective gravity will impose an additional, coherent distortion. It will very subtly stretch all those background galaxies, aligning their ovals in a specific direction, like leaves on the surface of a stream showing the direction of an unseen current. By measuring the shapes of millions of galaxies with extraordinary precision, scientists can perform a statistical analysis. They can filter out the random orientations and detect the systematic shear caused by the dark matter's gravitational pull. This allows them to create three-dimensional mass maps of the cosmos, charting the invisible filaments and halos directly. These maps are not artists' impressions, they are data-driven reconstructions of the dark matter web, built purely from the distorted light of the universe. Gravitational lensing is our most direct way of touching the dark universe. It lets us weigh galaxy clusters, confirm the collisionless nature of dark matter as seen in the bullet cluster, and trace the cosmic web in pure gravitational influence. We are literally using bent starlight to draw a picture of the invisible. This ability to map the dark web has revealed a fascinating and troubling puzzle right in our own cosmic backyard. Our Milky Way galaxy is not alone. It is surrounded by a swarm of small satellite galaxies, like moons orbiting a planet. But according to the magnificent cosmological simulations that so accurately predict the large-scale cosmic web, there is a glaring mismatch. The simulations tell us that thousands of small, dense clumps of dark matter should be orbiting our galaxy, each one a potential seed for a tiny dwarf galaxy. Yet when we look, we only see a few dozen. This is the missing satellites problem, and it is one of the most significant challenges to our standard model of cold dark matter. Where are all the little galaxies that should be there? The most compelling answer is not that the dark matter halos are missing, but that they are dark. A dark matter halo is just a gravitational potential well, a place where gas could collect and eventually form stars, but star formation is a delicate process. In these smallest halos, the gravitational pull is incredibly weak. If even a single massive star forms and explodes as a supernova, the energy released can easily overcome the halo's feeble gravity. The resulting shockwave can blow all the remaining gas clear out into intergalactic space, shutting down star formation for good. The halo remains a silent sphere of pure dark matter, invisible to our telescopes because it never managed to light a single star. This process, called supernova feedback, could explain why so many predicted halos are empty. Another possibility involves the very nature of dark matter itself. Could it be slightly warmer than we think? The standard cold dark matter model assumes particles that move slowly, allowing them to clump on very small scales. But if dark matter particles were born with a little more speed, dubbed warm dark matter, their motion would smooth out the smallest clumps. This would naturally produce fewer tiny halos, potentially bringing the simulations into better agreement with the sparse dwarf galaxies we see. The hunt for these elusive dark halos continues. Astronomers search for subtle ripples in the Milky Way's outer gas, or for faint, unexpected streams of stars that might have been torn from a dark satellite. Each discovery, or lack thereof, helps us refine the recipe. The missing satellites problem is not a failure of the dark matter theory, but a crucial test. It forces us to understand the intricate and often violent dance between the invisible scaffolding and the ordinary matter that tries, and sometimes fails, to shine upon it. The cosmic web simulations are a triumph of modern cosmology, but they also make very specific predictions about the shape of individual dark matter halos. When you zoom in on one of those simulated halos, the dark matter density should rise dramatically toward the center, forming a sharp peak or cusp. This makes intuitive gravitational sense as matter naturally piles up in the deepest part of the well. Yet when astronomers study real galaxies, especially faint, diffuse dwarf galaxies, they find something very different. The dark matter in their cores seems to be distributed in a gentle, flattened profile, more like a soft hill than a jagged peak. This mismatch is the cuspy halo problem, and it forces us to question what is happening in the mysterious hearts of galaxies. To understand the tension, think of a galaxy as a gravitational well carved by dark matter. In the pristine simulations, where only dark matter's gravity is at play, particles sink to the center and stay there, building that dense cusp. But the real universe is messier, filled with the ordinary matter of stars and gas. This baryonic matter doesn't just follow the dark matter's lead, it can talk back through complex, violent processes. When massive stars are born in the galactic center, they live fast and die young in colossal supernova explosions. These aren't just flashes of light, they are titanic energy releases that can churn the central gas, pushing it around in waves. This constant stellar feedback, this bubbling and boiling of ordinary matter, could be stirring up the dark matter gravitationally, effectively smoothing out the central cusp into a softer core over billions of years. It is a reminder that dark matter, while dominant, does not exist in a vacuum. Its final distribution might be sculpted by the fireworks of the stars it helped to create. Another possibility is more fundamental. What if the simulations are correct about gravity, but wrong about dark matter itself? The cusp prediction relies on dark matter particles being cold, slow, and collisionless. But if dark matter has even a tiny ability to interact with itself through some unknown force, those interactions could act like a form of friction. Particles in the crowded center would scatter off each other, transferring energy and preventing them from settling into such a steep density peak. Alternatively, if dark matter were born with a little more thermal motion, making it warm, that inherent motion would also resist the formation of a sharp cusp. The core-like centers we observe could be a direct signal that dark matter is not perfectly simple or perfectly cold. The cuspy halo problem sits at a fascinating crossroads. It may be a clue that we are finally seeing the complex dialogue between the dark universe and the luminous one, where stellar winds and explosions leave their mark on the invisible scaffold. Or it could be a sign that dark matter's own hidden physics is beginning to reveal itself in the quiet, diffuse light of the smallest galaxies. Each faint dwarf galaxy we map is not just a collection of old stars, it is a natural laboratory testing the rules of an unseen world. The temperature of dark matter isn't about heat in the way we feel it, but about the speed of its particles in the early universe. This simple idea of velocity splits the theoretical landscape into three distinct possibilities, each painting a different picture of cosmic history. The reigning champion is cold dark matter. Imagine particles that are heavy and sluggish, moving far slower than the speed of light when the first structures began to form. Because they are so slow, they readily clump together under gravity on every scale, from the tiniest halos to the grand filaments of the cosmic web. This model is spectacularly successful at predicting the universe's large-scale architecture, the very web we see in simulations and surveys. Its triumph is why cold dark matter forms the bedrock of our standard cosmological model, but as we've seen, its success on grand scales may come with small-scale headaches, like the missing satellites and the unexpectedly soft cores of dwarf galaxies. This is where the idea of warm dark matter enters the debate. Picture particles that are much lighter, born with more kinetic energy, zipping through the infant cosmos at a significant fraction of light speed. This inherent speed acts like a cosmic smoothing iron. It washes out the smallest density fluctuations, preventing dark matter from clumping on the scale of tiny dwarf galaxies. The result is a universe that still builds the massive cosmic web, but with far fewer of the smallest dark matter halos. This could naturally explain why we see fewer dwarf galaxies than cold dark matter predicts. Those missing satellites aren't missing. They were never able to form in the first place because the dark matter was too warm to settle into such small knots. The gentle cores we observe in dwarfs also fit more neatly with this smoother, warmer distribution. On the far end of the spectrum is hot dark matter, composed of particles moving at almost the speed of light from the very beginning. We know such particles exist. Neutrinos are a perfect example, but if hot dark matter were the dominant player, its incredible velocity would have prevented it from clumping at all until very late in cosmic history. Galaxies and clusters would have formed from the top down, with giant structures fragmenting into smaller ones, the opposite of what we observe. The cosmic web would look entirely different. Observations have definitively ruled out hot dark matter as the primary substance, though a sea of fast-moving neutrinos does make up a tiny, whisper-thin component of the cosmic mass. So, is the universe cold or warm? The debate is alive in cosmology today. The answer lies in the fine details of the cosmic web and the faintest galaxies. Future observations by telescopes like the Vera C. Rubin Observatory will map millions of dwarf galaxies and ultra-faint stellar streams around the Milky Way. The statistics of these tiniest structures will be a direct thermometer for the early universe. If we find a population of incredibly faint, diffuse galaxies, it would favor the cold model, suggesting feedback-suppressed star formation. If they remain starkly absent, the evidence would tilt toward a warmer, smoother beginning. We are, in essence, using the smallest surviving fragments of the cosmic dawn to measure the temperature of the dark. Deep beneath the rolling hills of South Dakota, in a place where silence is measured in particles, scientists are waiting for a ghost to touch the world. This is the Sanford Underground Research Facility, home to experiments like LUX Zeppelin, one of the most sensitive dark matter detectors ever built. Its mission is deceptively simple: to catch a single, fleeting interaction between a dark matter particle and an atom of ordinary matter. The principle hinges on the leading candidate, the WIMP. If these weakly interacting massive particles are real, they are streaming through Earth and through you right now, a cosmic wind of invisible matter. But because they interact so feebly, trillions pass through every square inch every second without a trace. The hope is that, very rarely, one might just bump into the nucleus of an atom. To have any chance of seeing such an impossibly faint event, you must go to extraordinary lengths. The detector itself is a marvel of purity. At the heart of LUX Zeppelin is a giant titanium tank filled with 10 metric tons of liquid xenon, chilled to -100 degrees Celsius. Xenon is chosen because it is a noble gas, stable and inert, and its large atomic nucleus presents a bigger target. If a WIMP strikes a xenon nucleus, the collision should produce two telltale signals: a quick flash of scintillation light and a jolt of electrical charge. Arrays of exquisitely sensitive light sensors, called photomultiplier tubes, line the top and bottom of the chamber, waiting to capture that single, precious photon. But here lies the true challenge. The universe is a noisy place. Cosmic rays from space, natural radioactivity from the surrounding rock, even trace radioactive elements in the detector materials themselves, all of these can mimic the signal of a dark matter collision. To silence this cacophony, the experiment is buried a mile underground, beneath a shield of rock that blocks most cosmic rays. The liquid xenon is repeatedly purified to remove every possible radioactive contaminant. The entire apparatus is then surrounded by a huge tank of ultra-pure water, which acts as a further shield and a veto system, helping to identify and reject any remaining background events that come from the outside. It is a cathedral of quiet, built to hear a whisper, and after years of listening, what have they heard? Nothing. The same profound silence echoes from other giant detectors around the world, like Zeno NNT in Italy and Panda X in China. They have not found a definitive signal. This null result is not a failure, it is a powerful form of discovery. Each experiment defines a new line on a map, ruling out vast territories of possibility. We now know that if WIMP exist, they must be even more weakly interacting or have a different mass than our best theories once suggested. The search is pushing the properties of dark matter into ever more extreme and exotic corners of parameter space. It forces us to ask, are we listening for the right kind of ghost, or is the universe hiding its secrets in a way we have not yet learned to perceive? While underground labs listen for a whisper, other scientists are scanning the heavens for a scream. This is the hunt for indirect detection, a search not for dark matter itself, but for the debris it might leave behind. The strategy hinges on a fascinating possibility. What if dark matter particles are their own antimatter counterparts? In the particle world, when matter meets its antimatter twin, they annihilate in a flash of pure energy, transforming into other particles. If dark matter has this property, then wherever these particles naturally collide within their dense halos, they could destroy each other, producing a shower of secondary signals we can actually see. These would be gamma rays, the most energetic form of light, or perhaps high-energy neutrinos and cosmic rays. We would not be catching the ghost, we would be finding its footprints in the sand. To conduct this search, astronomers use telescopes that see the universe in extreme energies. The Fermi Gamma Ray Space Telescope orbits Earth, scanning the entire sky for gamma-ray photons. Far below, at the South Pole, the Ice Cube Neutrino Observatory uses a cubic kilometer of ancient glacial ice as a detector, waiting for the rare flash of light produced when a neutrino from deep space interacts with an atom in the ice. These instruments turn the cosmos itself into a colossal laboratory. The most tantalizing clue from this search is known as the galactic center, XS. The heart of our Milky Way is predicted to be one of the densest reservoirs of dark matter in the galaxy. When the Fermi telescope mapped the gamma rays coming from this region, it found an unexpected and mysterious glow, a diffuse excess of gamma rays that couldn't be fully explained by all the known astrophysical sources, like spinning neutron stars called pulsars or the remnants of ancient supernovae. The signal's shape and energy matched what some models predicted for dark matter annihilation. For a time, it seemed we might be looking at the first indirect glimpse of the invisible substance. But the universe is rarely so straightforward. Further analysis revealed that the galactic center is a chaotic, crowded place. Thousands of unresolved pulsars, too faint to see individually, could collectively produce a very similar haze of gamma rays. Distinguishing between a dark matter signal and this astrophysical background is like trying to hear a single instrument in a roaring symphony. The excess remains an intriguing puzzle, a maybe that has not yet solidified into a yes. Every potential signal walks this fine line. A detection must be bulletproof, ruling out every conceivable ordinary explanation before we can claim a discovery from the dark. So the search continues, with scientists meticulously modeling the complex astrophysics of our galaxy while designing ever more sensitive next-generation telescopes. The hope is that by looking at quieter targets, like the faint dwarf galaxies orbiting the Milky Way, which are rich in dark matter but poor in confusing stellar fireworks, we might one day see an unambiguous flare of annihilation, a beacon from the invisible universe finally announcing its presence in a language of light we can understand. While underground detectors listen and telescopes scan for annihilation, there is a place where scientists try to create dark matter from pure energy. At the border between France and Switzerland, buried deep in a circular tunnel 17 miles around, lies the largest machine ever built, the Large Hadron Collider. This isn't a quiet observatory, it is a cosmic forge. Here, physicists take beams of protons, accelerate them to within a hair's breadth of the speed of light, and smash them together head-on. In these collisions, for a fleeting fraction of a second, temperatures and energies are recreated that haven't existed since the first moments after the Big Bang. The hope is spectacular that in this maelstrom of creation, we might not just find known particles, but actually manufacture the unknown ones, bringing dark matter into existence right before our eyes. The logic is powerful. If dark matter is made of particles like WIMP, they would have been produced copiously in the hot, dense early universe. By recreating those conditions, even in a microscopic volume, we might be able to produce them again. But this creates an immediate and profound challenge. By its very definition, dark matter does not interact with light or with the ordinary matter of our detectors. If we create it, how would we even know? The answer is a brilliant piece of detective work called missing transverse momentum. Imagine two protons racing toward each other from opposite directions. Their total forward momentum cancels out to zero. When they collide and shatter, the debris, a spray of familiar particles like quarks and photons, flies out in all directions. Physicists can measure the energy and momentum of every single piece of that debris with immense precision. The law of conservation of momentum dictates that all the energy going into the collision must be accounted for in the products coming out. So, if they see a collision where the debris seems to recoil to one side, as if something invisible and undetectable carried away a chunk of momentum in the opposite direction, that is the signature. It is the smoking gun of an unseen particle fleeing the scene. This missing energy is the ghost in the machine, a blank space in the data that screams of something new. The LHC's greatest triumph to date was, of course, the discovery of the Higgs boson in 2012, confirming the mechanism that gives other particles their mass. It was a monumental validation of the standard model of particle physics, but in the hunt for physics beyond that model, for the particles that make up dark matter, the collider has so far returned empty-handed. No unambiguous signal of missing transverse momentum has pointed to a dark matter candidate. This silence, much like the quiet in the underground labs, is itself a form of guidance. Each experiment at the LHC draws a new line in the sand, telling theorists that if dark matter particles are produced here, they must be heavier or interact even more weakly than our current setups can perceive. The machine is systematically closing doors, forcing us to reconsider the pathways to the dark sector. It tells us that if dark matter is a particle born from the energy of creation, it is more elusive or perhaps more cleverly hidden than our most powerful forge can yet reveal. The profound silence from particle colliders in underground labs forces us to ask a heretical question: what if we are not just searching for the wrong particle, but for the wrong thing entirely? What if the answer is not a missing substance, but a misunderstood force? This is the radical heart of the 13th mystery, a theory called modified Newtonian dynamics, or MEND. It proposes a breathtakingly simple alternative to dark matter: throw out the invisible stuff and change the rules of gravity instead. For over 3 centuries, since Newton watched his legendary apple fall, we have believed gravity's pull weakens with the square of the distance. This law works perfectly for planets, for spacecraft, and for apples, but MEND suggests that in the realm of the incredibly faint, where accelerations are vanishingly small, this law quietly breaks down. At the outer edges of a galaxy, the gravitational tug from all the stars at the center becomes extraordinarily weak. In this domain of extreme subtlety, MEND proposes that gravity does not fade away as quickly as Newton or even Einstein predicted. It gets a second wind. This tweak to the math is not arbitrary. It is tuned to a specific, tiny acceleration threshold, and with that single adjustment, something magical happens in the equations. The predicted rotation curves of spiral galaxies, the very data Vera Rubin used to prove dark matter's existence, snap perfectly into place. The stars at the edges whip around at the observed speeds, not because of an unseen halo of matter, but because gravity itself is stronger there than our standard laws allow. It is an elegant solution, solving the rotation curve problem without invoking a single ghostly particle. For its proponents, MEND is a triumph of Occam's razor, cutting away an entire unseen universe to fix a flaw in our understanding of the most familiar force. But elegance in one arena does not guarantee truth in all. When MEND is tested against the full cosmic evidence, it begins to fray at the edges. Recall the bullet cluster, the cosmic collision where the mass sailed clean through the visible gas. MEND struggles mightily to explain this. If there is no dark matter, then the mass must be where the visible matter is. but the lensing map shows the mass is not with the gas, it is somewhere else entirely. To salvage this, Mund would need to invent a new, invisible type of matter anyway, defeating its own central premise. The theory faces an even greater challenge from the cosmic microwave background. The intricate pattern of hot and cold spots in that ancient light is a precise record of how structures formed in the early universe. The standard model of cosmology, with its dark matter and dark energy, predicts these patterns with stunning accuracy. Mund, in its original form, cannot reproduce this detailed blueprint of the infant cosmos. It cannot easily explain how galaxies and clusters could have formed so quickly without the gravitational head start provided by dark matter's invisible scaffolding. This is the fundamental tension. Mund offers a beautiful, alternative explanation for one set of galactic puzzles, but it fails to account for the broader architecture of the universe revealed by collisions and the afterglow of creation. It is a compelling footnote, a reminder that our grasp of gravity may still be incomplete, but not yet a replacement for the dark universe it seeks to banish. The quest continues, not just to find what is missing, but to be certain we understand the rules of the game being played in the dark. Sometimes the clues come not from the distant cosmos, but from our own backyard. For decades, a pair of robotic explorers named Pioneer 10 and Pioneer 11 sailed silently toward the stars, carrying golden plaques etched with messages from humanity. But as they journeyed beyond the orbit of Pluto, mission controllers noticed something deeply perplexing. The spacecraft were slowing down. It was an almost imperceptible deceleration, a tiny tug back toward the sun equivalent to just 1/10,000,000th of the gravity we feel on Earth. Yet it was there, an unaccounted-for force acting on these human-made objects in the deep, dark quiet. This was the Pioneer anomaly, and for years it ignited the imagination of physicists. Could this be a sign of dark matter's gravitational pull within our solar system, a faint halo we had not detected, or was it the first subtle evidence that our laws of gravity needed revision, a hint of modified dynamics at the edge of our planetary neighborhood? The mystery lingered until a meticulous, years-long investigation pieced together a more mundane, yet brilliant answer. The Pioneers were powered by radioactive plutonium, and that decaying heat kept their electronics warm. Scientists realized this heat was radiating off the spacecraft asymmetrically, primarily from the back of their dish-shaped antennae. This thermal radiation, photons of infrared light carrying a tiny amount of momentum, was acting like a faint but constant photon rocket, gently pushing the craft backward. Once this subtle thermal recoil was precisely modeled, the anomalous deceleration vanished. The Pioneer anomaly was solved, a testament to human ingenuity in tracking down every last whisper of force in the void. Yet its legacy is a reminder of how even the smallest discrepancy can point our gaze toward the profound. Other oddities persist. There is the curious flyby anomaly, where certain spacecraft, like NASA Galileo probe, have experienced tiny, unexpected changes in speed as they slingshot around Earth for a gravity assist. The shifts are minuscule, mere millimeters per second, but they appear in the data. Then there is the controversial observation of some widely separated binary star systems. According to standard gravity, stars orbiting each other at great distances should move more slowly, yet a handful of studies suggest these wide binaries seem to orbit as if held by a stronger gravitational grip, a finding that some researchers argue aligns with modified gravity theories like Mund rather than dark matter. These signals from the local universe are faint, hotly debated, and far from confirmed. They live in the messy borderland where measurement error, unmodeled conventional physics, and the potential for true revolution all collide. But that is where discovery often begins, with a stubborn little detail that refuses to fit. a quiet anomaly whispering that there is still so much we do not understand about the force that binds the cosmos. For centuries, the central question of cosmology was simple: would the universe expand forever, or would gravity eventually pull everything back together in a fiery collapse? The answer seemed to hinge on a cosmic tug-of-war between the outward momentum of the Big Bang and the relentless inward pull of all the matter in the cosmos. Then, in the late 1990s, two independent teams of astronomers made a measurement that shattered this entire paradigm. They were using the universe's most reliable mile markers, a special kind of exploding star called a Type Ia supernova. These stellar explosions are remarkable because they all reach roughly the same peak brightness, a standard candle. By measuring how bright they appear from Earth, astronomers can calculate their true distance with incredible precision. And by analyzing the color or redshift of their light, they can determine how much the universe has stretched since the explosion occurred. By comparing distances and redshifts for supernova billions of light years away, the teams, led by Saul Perlmutter and by Brian Schmidt and Adam Rees, were mapping the expansion history of the universe. They fully expected to confirm that gravity was putting the brakes on, that the expansion was slowing down over time. What they found was the opposite. The most distant ancient supernovae were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious repulsive force, acting against the pull of gravity on the largest scales, was stretching the fabric of space itself faster and faster. The discovery was so shocking that both teams spent years checking and rechecking their data, searching for errors in dust absorption or stellar evolution. But the evidence was undeniable. In 1998, they announced their findings to a stunned scientific world. For revealing this accelerating expansion, they were awarded the Nobel Prize in Physics in 2011. The cause of this cosmic acceleration was given a name that echoed the other great unknown, dark energy. It was not a substance like dark matter, but a property of space, a relentless pressure embedded in the vacuum itself. In one stroke, the fate of the universe was rewritten. Gravity was no longer the sole ruler of cosmic destiny. A deeper, more dominant force was now in charge, and we had no idea what it was. That accelerating expansion demanded a source, a name for the force that was winning the cosmic tug-of-war. The leading candidate is an idea with a famously troubled past, Einstein's cosmological constant. Represented by the Greek letter lambda, it is the simplest mathematical term you can add to the equations of general relativity. Its meaning is both profound and strange. It represents a constant energy density woven into the very fabric of empty space itself. Think of the vacuum not as a true nothing, but as a seething quantum foam where virtual particles flicker in and out of existence in a heartbeat. According to quantum field theory, this frantic activity should endow every cubic centimeter of so-called empty space with a tremendous intrinsic energy, a pressure that pushes outward. This vacuum energy is the physical embodiment of the cosmological constant, a repulsive force that is an inherent property of the cosmos. The irony of this explanation is rich. Einstein originally invented the cosmological constant for the opposite reason. When he applied his new theory of gravity to the entire universe, he believed, like most scientists of his time, that the cosmos was static and eternal. But his equations insisted that a universe full of matter should either be expanding or contracting under gravity. To force a static solution, he inserted lambda as a kind of anti-gravity, a repulsive term to precisely balance the inward crush, holding the universe in a precarious, unchanging equilibrium. When Edwin Hubble later discovered the universe was in fact expanding, Einstein famously discarded the constant, calling it his greatest blunder. he had missed the chance to predict cosmic expansion. Now, nearly a century later, that rejected idea has made a spectacular comeback. The observed acceleration of the universe fits perfectly with a positive cosmological constant, a small but relentless repulsive energy inherent to space. It is the frontrunner not because it is elegant, but because it works, matching a vast array of observational data with just one number. Yet this resurrection comes with a catastrophic problem, a discrepancy so vast it is often called the worst prediction in the history of physics. When theorists calculate how much vacuum energy should be generated by all those quantum fluctuations, the number they get is absurd. It is 10 to the power of 120 times larger than the value we actually observe from the accelerating expansion. That is not a small error, it is a 1 followed by 120 zeros. If the theoretical prediction were correct, the repulsive force of the vacuum would have been so unimaginably powerful in the early universe that not a single atom, not a single star or galaxy could ever have formed. Space would have blown itself apart in an instant. The fact that we exist, that we see a universe of structure, tells us our understanding is profoundly broken. Either something is drastically wrong with our theory of quantum mechanics on cosmic scales, or there is a miraculous, unexplained cancellation happening, fine-tuned to 1 part in 10 to the 120th power. The cosmological constant is both our best answer and a glaring sign that a deeper truth lies completely hidden from view. The cosmological constant's staggering fine-tuning problem forces us to consider a more dynamic possibility. What if dark energy is not a fixed property of the vacuum, but something that evolves? This is the compelling idea of quintessence, a theoretical energy field that permeates all of space, much like the cosmological constant, but with a crucial difference: its energy density can slowly change over time. The name itself is a poetic nod to the ancient philosophical concept of a fifth element, beyond earth, air, fire, and water, that fills the universe. In modern cosmology, it represents a fluid, breathing alternative to a static lambda. Think of it not as a rigid feature of space, but as a kind of cosmic weather, a pressure that can subtly strengthen or weaken as the cosmos ages. This dynamism offers a potential escape from the fine-tuning nightmare. Instead of requiring a miraculously perfect cancellation from the first instant, a quintessence field could have started with a much higher energy that naturally diluted and decayed over billions of years, only recently becoming the dominant force we measure today. In this way, the acceleration we see is not an eternal truth, but a phase in the life of the universe, a chapter we happen to be living in. The concept is deeply familiar to cosmologists because it echoes the most successful idea in early universe physics: inflation. Just moments after the Big Bang, a similar repulsive field, called the inflaton, is believed to have powered a period of hyper-fast expansion, smoothing and flattening the entire cosmos before fading away. Quintessence is like a distant, much weaker cousin of that inflaton field, one that has been simmering in the background for eons, only now making its presence known as the matter density of the universe thins out. This family resemblance is both inspiring and challenging. It shows the concept is plausible within our theoretical toolkit, but it also means we are invoking a second mysterious field to explain the cosmos, on top of the inflaton and dark matter. How could we possibly tell if dark energy is a constant lambda or a dynamic quintessence? The test lies in the history of expansion itself. A true cosmological constant pushes with unchanging strength, so its repulsive effect becomes more dominant as the universe expands and matter dilutes. A quintessence field, however, could behave differently. Its pressure might vary, perhaps weakening over time or even changing its character from repulsive to attractive in the far future. To detect this, astronomers look for tiny deviations in how the expansion has accelerated across cosmic time. They use the same celestial mile markers, type Ia supernova, but now they compare them across even wider ranges of distance and age, building a detailed movie of the universe's expansion rate over billions of years. They also turn to colossal maps of the large-scale structure, like those from the Dark Energy Survey or the future Euclid Space Telescope. The growth of galaxy clusters and the stretching of the cosmic web are also sensitive to the precise push of dark energy throughout history. If the data ever shows a clear signal that the strength of dark energy was different in the past than it is today, it would be a monumental discovery. It would mean dark energy is alive, a changing force, and the cosmological constant would be dethroned. We would then embark on a new quest to understand the nature of this quintessence field, its origins, and its ultimate fate, rewriting not just our present, but the entire timeline of the cosmos. This disagreement over the speed of the universe's expansion is more than a minor calibration error. It is a full-blown crisis in cosmology known as the Hubble tension. At its heart is a single, crucial number, the Hubble constant, represented as h0. This figure tells us how fast the universe is expanding today, the current rate at which galaxies are rushing apart from each other. Pinpointing this number should be a straightforward measurement, but it has become a source of deep and growing conflict. Two different, highly precise methods for measuring h0 are now giving stubbornly different answers, and the gap between them is too large to be explained by simple error. It is a crack in the foundation of our cosmic model. The first method looks back to the very beginning, using the cosmic microwave background as its guide. The Planck satellite mapped the subtle temperature fluctuations in this ancient light with exquisite detail. By feeding this pattern into our standard model of cosmology, which includes dark matter and a cosmological constant for dark energy, scientists can run the cosmic movie forward. The model tells us exactly how the universe should have evolved from that smooth, hot soup into the structured web we see today, and crucially, it predicts what the expansion rate should be right now. This early universe method yields a Hubble constant of about 67 kilometers per second per megaparsec. In simpler terms, it means for every megaparsec, a distance of about 3.3 million light-years, a galaxy is moving away from us at 67 kilometers per second faster. This result is incredibly precise, with a margin of error of less than 1%. The second method works in the local, modern universe. It relies on building a cosmic distance ladder, a step-by-step process to measure how far away things are. The first rung uses a special class of stars called Cepheid variables. These stars pulse with a regular rhythm, and the period of their pulsation is directly tied to their true brightness. By measuring their pulse rate from Earth, astronomers know their intrinsic luminosity. Comparing that to how dim they appear gives a direct measurement of their distance. The next rung uses type Ia supernova. These stellar explosions, as we've learned, are brilliant standard candles. By finding Cepheid variables in the same galaxies as these supernovae, scientists can calibrate the supernova's true peak brightness with phenomenal accuracy. Once calibrated, they can use these supernovae to measure distances to galaxies far across the cosmos. By combining these distances with measurements of how fast those galaxies are receding from us, their redshift, astronomers can calculate the Hubble constant directly. This late universe method, championed by teams using the Hubble Space Telescope, gives a value of about 73 kilometers per second per megaparsec. That is roughly 5 to 10% faster than the early universe prediction. The numbers are close, but their uncertainties do not overlap. This is not a case of blurred lines. It is a clear and persistent discrepancy that has survived over a decade of increasingly precise observations. The implications are profound. If both measurements are correct, and there is no sign of a major mistake in either camp, then our standard model of cosmology is incomplete. Something is missing from the equations we used to extrapolate from the infant universe to today. The tension could be a clue pointing to new physics. Perhaps dark energy is not a simple cosmological constant, but a dynamic quintessence field that changed strength over cosmic history, subtly altering the expansion rate. Maybe there is an extra, unknown type of neutrino or other lightweight particle that added a burst of extra energy to the early universe, changing its evolution. Or it could hint at something even more exotic, like a flaw in our understanding of gravity itself on the largest scales. The Hubble tension is more than a technical dispute. It is the universe presenting us with a puzzle it insists we solve, a direct challenge to our story of how everything works. The Hubble tension is a direct challenge, forcing us to question the very timeline of the cosmos, but zoom out further, and this question of how fast the universe expands becomes a question of how it will all end. The nature of dark energy doesn't just dictate the present expansion rate, it writes the final chapter for everything that exists. Our ultimate fate hinges on a simple but profound unknown. Is dark energy constant? Does it grow, or does it fade? If the cosmological constant model is correct, and dark energy is a fixed, unchanging property of space, then the future is one of relentless, lonely expansion. This is the path to the Big Freeze, also known as heat death. As space stretches faster and faster, galaxies beyond our local group will vanish over the cosmic horizon, their light never able to reach us again. Within each surviving island of stars, stellar furnaces will eventually burn out. Black holes will slowly evaporate over incomprehensible eons through Hawking radiation. Matter itself may decay. The universe will approach a state of maximum entropy, a uniform, frigid sea of diluted particles and radiation where no energy can be harnessed, no structure can form, and no new story can ever begin. It is a quiet, cold, and eternal end, but if dark energy is the dynamic field of quintessence, the future could be far more dramatic. One terrifying possibility is called phantom dark energy. In this scenario, the energy density of the dark energy field doesn't just stay constant, it actually increases over time. The repulsive force would grow stronger and stronger, accelerating the expansion at a rate that becomes infinite. The result is the Big Rip. Imagine a force that doesn't just push galaxies apart, but eventually overcomes every force that holds things together. Billions of years before the end, galaxy clusters would be torn apart. Then individual galaxies would be shredded. In the final months, stars would be ripped from their orbits. In the last minutes, planets would be pulled apart. In the final horrific instance, the phantom energy would overwhelm the very nuclear forces binding atoms together, dissolving all matter into a soup of disconnected elementary particles. The fabric of spacetime itself would be torn asunder. It is an end of unimaginable violence. There is, however, a third possibility, one that flips the script entirely. What if quintessence is not a phantom, but a field that weakens and decays over time? If its repulsive push fades away, the ancient tug-of-war could swing back in gravity's favor. The expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward each other. The universe would start to collapse. Temperatures and densities would rise as all matter and energy are compressed into an ever smaller volume. This is the Big Crunch, a cosmic mirror image of the Big Bang, ending in a singularity of infinite density. Some theories even suggest such a crunch could trigger a new Big Bang, a cyclical universe of endless rebirth, a cosmic phoenix. So which will it be, a freeze, a rip, or a crunch? The answer is encoded in the precise behavior of dark energy, in that subtle W that astronomers measure. The data so far is consistent with a simple cosmological constant, pointing toward the big freeze, but the error bars are still wide enough to allow for the phantom or decaying scenarios. Every new supernova measured, every deeper map of the cosmic web, is a vote for our ultimate destiny. We are living in the brief, golden age where we can still see the evidence, where the light from distant galaxies still reaches us, allowing us to read our own epitaph written in the expanding sky. The mystery of dark energy is, ultimately, the mystery of our own ending. That final chapter is written in the very arrangement of the galaxies we see today. To read it, we must learn to measure the universe with a ruler stamped into the cosmos at its birth. This is the 20th mystery, the story of baryon acoustic oscillations. Long before the first stars flickered, the universe was a seething, opaque plasma, a tightly coupled soup of ordinary matter and light. In that dense medium, gravity acted as a constant pull, trying to make regions collapse, while the intense radiation pressure from the trapped photons pushed back out. This push and pull set the entire cosmos ringing like a bell, generating colossal sound waves that raced outward from every slight overdensity at nearly half the speed of light. For nearly 400,000 years, these pressure waves expanded through the primordial plasma, creating spherical ripples of compressed matter and energy. Then, in the moment of recombination, when atoms formed and the fog cleared, the music stopped abruptly, the waves were frozen in place, each ripple became a spherical shell, with matter slightly more concentrated at its edge. The radius of that shell was fixed by how far sound could travel before the universe became transparent, a distance of about 500 million light years. This scale became a cosmic fossil, a standard ruler imprinted on the distribution of matter. Today, that ruler is visible in the way galaxies are spaced. Because galaxies are more likely to form from the denser regions left behind by those ancient waves, there is a subtle statistical preference for pairs of galaxies to be separated by that specific 500 million light-year scale. It is not that you can point to one perfect ring of galaxies in the sky, but by mapping the positions of millions of galaxies, a distinct peak emerges in the data, a faint echo of that primordial sound. This baryon acoustic oscillation peak is a gift to cosmologists. It is a ruler of known length, etched across the entire sky. By measuring how this apparent ruler looks at different distances, and therefore at different epochs in cosmic history, astronomers can perform a breathtaking measurement. They can see how the geometry of space itself has stretched over time. If dark energy has been strengthening or weakening, it will change how that 500 million light-year standard ruler appears to us when we look far back in time. Current galaxy surveys, like those from the Sloan Digital Sky Survey, have used this technique with extraordinary precision. They confirm the accelerating expansion and tightly constrain the properties of dark energy, lending independent and powerful support to the findings from supernova. This frozen echo from the universe's first sound gives us a direct, three-dimensional map of how the cosmos has grown, offering a silent but definitive testimony to the force that now governs its fate. Even the oldest light in the universe carries the scars of its long journey. As the cosmic microwave background radiation traveled for billions of years to reach our telescopes, its photons did not sail through empty, static space. They passed through the growing cosmic web, the vast network of galaxy clusters and dark matter filaments. Each time a photon fell into a deep gravitational well created by one of these massive structures, it gained a tiny burst of energy, becoming slightly hotter. When it climbed back out, it lost that energy, cooling back down. In a universe where matter was completely dominant and these gravitational wells remained constant over time, the gains and losses would perfectly cancel out. The photon would arrive at Earth with no net change, but we do not live in that universe. We live in a cosmos where dark energy has taken control. As the universe accelerates, the gravitational wells of the large-scale structure are not static. They are slowly weakening, being stretched and diluted by the expanding space. This changes the photon's journey in a subtle but profound way. When the photon falls into a well, it gains energy as usual. But by the time it climbs out, the well has become slightly shallower due to the influence of dark energy. The climb out is therefore not as steep, so the photon does not lose all the energy it gained. It arrives with a tiny, leftover amount of heat. Conversely, a photon passing through a large, under-dense void would lose energy falling into that gravitational hill and not fully regain it climbing out, leaving it slightly colder. This minuscule imprint is called the integrated Sachs-Wolf effect, and it is a direct signal of the changing gravitational landscape of a dark energy-dominated cosmos. Detecting this whisper-thin effect is a monumental challenge, as it requires comparing the detailed temperature map of the cosmic microwave background with a three-dimensional map of the universe's large-scale structure from galaxy surveys. The statistical correlation between the two, the slight tendency for hotter CMB spots to align with massive clusters and colder spots with vast voids, has been tentatively observed. It is another independent line of evidence, not for the expansion itself, but for the specific cause, a repulsive force that is actively smoothing out the universe's gravitational hills and valleys over time. This effect tells us that dark energy is not a passive background actor. It is a dynamic force, actively rewriting the gravitational potential of the entire cosmos as we speak. We happen to live at a moment of perfect cosmic balance. For nearly the entire history of the universe, dark matter was the undisputed ruler, its gravity patiently sculpting galaxies and clusters. And for almost all of the future that awaits, dark energy will be the absolute sovereign, its repulsive push diluting all structure into a cold, thin haze. Yet here we are in this fleeting sliver of time when the two titans are locked in a near tie. The energy density of dark matter and the energy density of dark energy are, within an order of magnitude, roughly the same. This is the cosmological coincidence problem, and it feels profoundly strange why now, of all the trillions upon trillions of years the cosmos will exist, why do conscious observers find themselves in this brief transitional epoch, this cosmic yesterday when the two great unknowns are comparable in strength? It seems like an incredible piece of luck, a special ticket drawn in a lottery of time. One interpretation is the anthropic principle, a philosophical idea that the universe we can observe must be compatible with the existence of observers. In a vast multiverse, where countless universes bubble into existence with different physical constants and different timelines, we naturally find ourselves in one where the conditions allowed galaxies, stars, planets, and ultimately life to form. If dark energy had been much stronger earlier, it would have blown apart the primordial soup before any structure could coalesce. If dark matter had been much weaker, galaxies might never have gathered at all. So perhaps our present moment isn't a random accident, but a necessity. We are here to ask the question because the cosmic ledger had to balance in this very specific way to make our existence possible. It is a compelling, if somewhat dizzying, perspective, yet many physicists search for a more satisfying, physical explanation. Could this coincidence be a clue that dark matter and dark energy are not independent strangers, but two faces of a single, deeper phenomenon? Some theoretical models propose a direct interaction between them, a kind of cosmic dialogue where one can slowly decay into the other. In such a scenario, the fact that their densities are similar today isn't a random snapshot, but a predictable phase in a long, intertwined evolution. The crossover we are witnessing would be an inevitable milestone, not a freak accident. The search for an answer lies in the data. If dark energy is a true constant, then the coincidence remains a stark, unanswered puzzle of timing. But if future observations find that dark energy is dynamic, that its strength has evolved in a specific way tied to the density of matter, then the coincidence might dissolve into a beautiful, interconnected mechanism. We are left wondering if our privileged view of this cosmic handoff is the universe's way of giving us a hint, a fleeting chance to see both architects at work before one fades forever into the dark. That cosmic coincidence, the strange balance of power we witness today, begs for a deeper connection. Could it be that dark matter and dark energy are not separate entities at all, but two different expressions of a single, unified dark sector? This is the tantalizing possibility behind the 23rd mystery, a quest for a theory that ties the entire dark universe together. The most elegant of these ideas imagines a single exotic substance, a cosmic fluid that changes its character over time. One candidate is known as the Chaplain gas. Picture a strange, unified dark fluid that fills the cosmos. In the dense, crowded universe of the distant past, this fluid would have behaved just like cold, dark matter. It would have clumped together under gravity, forming the halos and filaments that seeded galaxies, but as the universe expanded and thinned out, this same fluid would have undergone a profound transformation. Its internal pressure would change, turning from neutral or slightly attractive to strongly repulsive. In this late time phase, it would act exactly like dark energy, driving the accelerated expansion we see today. It is a beautifully parsimonious idea, one single component replacing two colossal unknowns. A universe filled with Chaplain gas would naturally evolve from a matter-dominated era to a dark energy-dominated era, potentially explaining the coincidence of why their densities are comparable now. It is a cosmic chameleon, wearing the mask of structure builder in its youth and the mask of cosmic accelerator in its old age, but the universe rarely allows for such simple elegance without a cost. When astronomers test the Chaplain gas model against precise observations like the cosmic microwave background and the large-scale structure, it struggles to fit all the data simultaneously. It often fails to reproduce the exact details of how galaxies cluster or the specific sound horizon scale seen in baryon acoustic oscillations. The data seems to prefer a universe where dark matter is truly cold and collisionless, and dark energy is a nearly constant vacuum energy. This has led theorists to consider more complex, but perhaps more realistic, models where dark matter and dark energy remain distinct, yet talk to each other. These are the interacting dark energy models. Imagine if dark matter particles were not perfectly stable. What if, over billions of years, they could slowly decay into dark energy? Or perhaps the two sectors are coupled by an unknown force, allowing them to exchange energy like two cosmic reservoirs connected by a hidden pipe. In one scenario, dark matter decays, subtly feeding the dark energy field and making it grow stronger over time. In another, dark energy might siphon energy from dark matter, causing it to dilute faster than expected as the universe expands. These interactions could subtly alter the expansion history of the universe and the growth of cosmic structure in ways that might, in principle, resolve tensions like the Hubble constant discrepancy. They offer a dynamic mechanism to explain why we see a balance today. It is not luck, but the result of a long, slow energy transfer that has brought the two densities into a temporary alignment. Yet, like all ambitious ideas, they are tightly constrained by the unforgiving light of observation. Any significant interaction between the dark sectors leaves an imprint. It changes how quickly galaxy clusters form over cosmic time. It alters the way the cosmic microwave background looks. Our increasingly precise maps of the universe act as a strict referee. So far, the data shows no clear signal of such an interaction. The simplest model, with non-interacting cold dark matter and a cosmological constant, still fits the vast tapestry of evidence best. These unifying theories remind us that our current picture, with two separate dark components, might be a temporary, clumsy framework. We may be describing the symptoms of a single, deeper illness we do not yet understand. The search for a connection is the search for a more fundamental law, one that would rewrite the dark chapters of our cosmic story with a single, elegant equation. Our maps of the cosmos reveal a universe of stunning contrast. We have focused on the glittering nodes of the cosmic web, the galaxies and clusters where matter concentrates. But between those threads lie the true titans of empty space, the cosmic voids. These are not mere gaps, they are immense, spherical regions of profound nothingness spanning hundreds of millions of light years. Within them, you might find only a handful of lonely, dim galaxies. To fly through a void would be a journey of unimaginable emptiness, where the nearest major galaxy cluster would be a faint, unreachable smudge on the horizon. This is not a smooth, uniform universe. It is a frothy, lumpy, and deeply textured reality, and this simple observation leads to a radical challenge to the dark energy paradigm. Could the accelerating expansion we measure be, at least in part, a grand cosmic illusion? The theory is known as backreaction. For a century, cosmologists have built their models on a foundational simplification that on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every point. This assumption allows for the elegant equations of general relativity that describe an average, smooth universe, but we do not live in that average universe. We live inside a specific structure, the local group of galaxies, which itself resides on the fringe of the vast Laniakea supercluster, which is, in turn, just one thread next to a staggering void. The backreaction idea asks a profound question: what if the lumpiness of the real cosmos changes how space itself expands from our particular vantage point? Think of it like this: gravity behaves differently in dense regions than in empty ones. Within a massive galaxy cluster, gravity's pull is fierce, strongly resisting the overall expansion of space. Inside a vast void, however, there is very little matter to pull back, so the empty space within the void can expand faster than the cosmic average. We are not floating in a perfectly smooth fluid, we are embedded in a complex landscape of mountains and caverns. If you were a tiny creature living deep inside one of those caverns, your measurement of how fast the cavern walls are moving apart might not accurately reflect the expansion rate of the entire mountain range. Some theorists propose that our position in the cosmic web, on the edge of structure, might skew our observations. The faster expansion of the giant voids nearby could, in effect, pull on the fabric of space around us, creating a local mimic of cosmic acceleration. In this view, dark energy might not be a mysterious new force, but a sign that we have incorrectly averaged a lumpy universe. It is a compelling argument from sheer geometry. Could we have been fooled by the architecture of our own home? The mathematics of backreaction is ferociously complex, modeling the gravitational interplay of billions of evolving structures. While the concept is intellectually powerful, most detailed calculations to date suggest a sobering result. The backreaction effect from cosmic structures is real, but it appears to be far too small to account for the full, robust signal of acceleration we see from supernova and the cosmic microwave background. It might contribute a minor percentage, a subtle tweak to the expansion rate, but not the dominant, driving repulsion we call dark energy. The voids are expanding faster, but not nearly fast enough to explain the data. This doesn't diminish the importance of the idea. It forces cosmology to grow up, to move beyond the simplistic smooth universe approximation and grapple with the real, gritty texture of the cosmos. Future surveys that map both galaxies and voids with unprecedented precision We'll put exact numbers on this backreaction effect. We will learn precisely how much our lumpy universe distorts our view. It is a crucial correction, a reminder that we must see the universe not as an abstract equation, but as a specific place with a specific address in the grand and frothy web of all things. The only way to test a recipe for the entire cosmos is to build a universe from scratch. This is the staggering ambition of cosmological simulations, where the laws of physics become lines of code and supercomputers run the clock forward over 13 billion years. Projects like Illustris TNG and Eagle are not video games, they are the most sophisticated virtual laboratories in existence. Their starting point is the near-uniform glow of the cosmic microwave background. Into this digital primordial soup, scientists input our best understanding of gravity, hydrodynamics, and the precise cosmological recipe: 26% cold dark matter and 68% dark energy. Then they press play. What unfolds is a breathtaking Genesis story. Trillions of particles, representing dark matter and ordinary gas, begin their gravitational dance. Dark matter clumps first, weaving the cosmic web. Gas flows along these invisible filaments, cooling and collapsing into the first stars within the dark matter halos. These stars die and explode, their supernova blasting gas back out into space, enriching it with heavy elements for the next generation. Black holes form at the centers of galaxies, swallowing material and firing colossal jets of energy that can heat or eject surrounding gas, regulating star formation. The simulation must account for all of this, a symphony of physics playing out across a virtual volume billions of light-years wide. The result, after months of computation, is a fully formed digital universe, complete with realistic-looking spiral and elliptical galaxies, galaxy clusters, and vast, empty voids. We can fly through it, pausing at any moment in cosmic history. This is not just a pretty picture, it is a critical test. By comparing the statistical properties of the virtual galaxies to the painstaking maps from real telescopes, we can see if our recipe is correct. Do the simulated galaxies have the right masses, the right shapes, the right distribution in space? The agreement is often remarkable, a powerful validation that our standard model of cosmology is on the right track. But the simulations also reveal where our models fail, spotlighting the cracks in our understanding. The dwarf galaxy problem is a prime example. While these simulations beautifully reproduce massive galaxies, they still struggle to get the smallest galaxies right. The simulated dwarfs often end up with overly dense cores and too many stars, or they appear in greater numbers than we observe around galaxies like our Milky Way. This mismatch is not a bug, it is a feature, a crucial clue. It tells us that the physics of star formation in these tiny, fragile halos is incredibly complex. Perhaps supernova feedback is even more violent than we model, or maybe dark matter has properties, like being slightly warm, that affect the smallest scales first. Every discrepancy is a signpost, pointing theorists toward the missing pieces in our cosmic puzzle. These virtual universes are our proving grounds, allowing us to run experiments we could never perform in reality. What if dark matter interacts with itself? What if dark energy is not constant? We can change a single parameter and watch the entire history of a universe unfold to see if it still looks like our own. In the silent hum of a supercomputer, we are not just observing the cosmos, we are learning to build it, one line of code at a time. The silent hum of our supercomputers can only take us so far. They're virtual universes built on the assumptions we feed them. To break the deadlock, to move from simulation to revelation, we need new eyes on the sky. The next decade will launch a fleet of cosmic observatories unlike any before, a coordinated global assault on the dark universe's deepest secrets. At the forefront is the Vera C. Rubin Observatory, perched on a mountaintop in Chile, its mission is one of pure, breathtaking scope to conduct the legacy survey of space and time. Every few nights for 10 years, its giant mirror and 3.2 billion pixel camera will capture an image of the southern sky so deep it could spot a golf ball on the moon. This relentless scan will catalog over 20 billion galaxies and measure the shapes of billions more. Why such an immense census? It will create the ultimate map for weak gravitational lensing. By seeing how the shapes of all those distant galaxies are subtly, coherently stretched by the intervening dark matter web, scientists will produce a three-dimensional mass map of the cosmos with unprecedented detail. It will also pinpoint the baryon acoustic oscillation scale across cosmic time with phenomenal precision. The LSSD will not just look at the dark universe, it will take its fingerprint. Meanwhile, from the vantage of space, the Nancy Grace Roman Space Telescope will open a different window. With a field of view 100 times larger than Hubble's, Roman will perform wide, deep surveys to hunt for Type Ia supernova by the thousands. It will find these cosmic mile markers farther back in time and with less interference from cosmic dust, building the most precise movie of the universe's expansion ever made. Its sharp infrared vision will also peer through dust to study how galaxy clusters grew over time, another critical test of dark energy's influence, and it will not work alone. Already in space, the European Euclid telescope is mapping the geometry of the dark universe using a combination of weak lensing and galaxy clustering. Back on Earth, the Dark Energy Spectroscopic Instrument DESI is not taking pictures but capturing the spectra of tens of millions of galaxies, measuring their redshifts to construct the largest three-dimensional map of the large-scale structure yet, revealing the imprint of dark energy on the cosmic web. This is not a series of separate experiments, it is a single, multifaceted campaign. Rubin's immense lensing map, Roman's pristine supernova history, Euclid's geometric survey, and DESI's spectroscopic web will all cross-check and reinforce each other. If dark energy is dynamic, if it has changed strength over the eons, this coordinated effort will catch it in the act. If the Hubble tension is a sign of new physics, these observatories will trace its source. We are on the cusp of moving from an era of mystery into an era of measurement. The data that will flood in over the next 10 years holds the potential to crack the cosmological code, to tell us whether we live in a universe ruled by a simple constant, a dynamic field, or something stranger still. The architects of the dark cosmos are about to have their blueprints examined under the brightest lights we have ever built. Our own cosmic backyard holds a faint, whispering particle that blurs the line between the known and the unknown. These are neutrinos, the closest thing we have to a familiar dark particle. Trillions of them pass through your body every second, ghostly remnants from the Big Bang and the furnaces of stars, interacting so rarely they might as well be shadows. For a time, they were a serious candidate for hot dark matter. Their incredible speed and weak interactions fit the profile of a substance that could shape the cosmos. But detailed observations of the cosmic microwave background and the large-scale structure delivered a clear verdict. Neutrinos are real, but they are far too light and fast to be the main architect. Their relentless motion would have smoothed out the early universe too much, preventing the beautiful, clumpy web of galaxies from forming in the way we so clearly see it today. Neutrinos exist, but they are a mere seasoning in the cosmic soup, comprising less than 1% of the total mass energy budget, yet even as a minor ingredient, they leave a subtle fingerprint on everything. Because they zip through the universe at nearly the speed of light for eons, they act as a kind of cosmic pressure, resisting gravity's pull on the very smallest scales. This means that the first structures to form in the universe were slightly larger than they would have been if neutrinos were completely massless. They imprinted a specific signature on the clustering of galaxies, a signature that our most precise surveys are now measuring. This brings us to a profound present-day puzzle. We know neutrinos have mass, but we do not know exactly how much. Experiments here on Earth have detected them oscillating, changing from one type to another, which proves they have mass. But these experiments can only measure the differences between their masses, not the absolute scale. Are they all incredibly light, or could one be significantly heavier? The answer matters deeply for cosmology. The exact mass of neutrinos changes how they dampen the growth of the smallest structures in the early universe. This, in turn, affects our measurements of other fundamental parameters, like the Hubble constant. Some cosmologists have proposed that if the heaviest neutrino has a mass at the very top of the allowed range, it could subtly alter the expansion history of the universe in a way that helps bridge the gap between the early and late measurements, easing the Hubble tension. It is a tantalizing possibility that a particle we can barely detect might hold a key to one of our biggest cosmological crises. Neutrinos are a humbling reminder. They are a genuine piece of the dark sector we have actually caught, particles that are everywhere yet almost impossible to grasp. Their story tells us that the universe is filled with elusive actors, and even the ones we know can still surprise us, their quiet whispers potentially holding echoes of the cosmos's deepest secrets. The fine-tuning of the cosmological constant is so impossibly precise it feels like a message. Perhaps it is not a problem to be solved by physics, but a selection effect written into the nature of reality itself. This brings us to one of the most speculative and profound ideas in modern science, the multiverse. The concept emerges not from cosmology alone, but from our most ambitious attempt at a theory of everything, string theory. In this framework, the fundamental particles are not points, but tiny, vibrating strings. The way a string vibrates determines whether it manifests as an electron, a quark, or a photon. But for the math to work, string theory requires more dimensions than the 3 of space and 1 of time we experience. The extra dimensions are thought to be curled up or compactified at scales far smaller than an atom. And here lies the catch: there are potentially an astronomical number of ways for these extra dimensions to curl up. Each unique configuration yields a different set of physical laws and constants for its corresponding universe, including a different value for the vacuum energy, our cosmological constant. This is the string theory landscape, a vast, perhaps infinite, collection of possible universes, each with its own unique physics. In this picture, our universe is not special, it is simply one possibility among a near infinity of others. In the overwhelming majority of these universes, the vacuum energy is enormous. In those worlds, space repels itself with such violence that galaxies, stars, and planets never coalesce. They are sterile, empty, and lifeless, but in a vanishingly small fraction of the landscape, by pure chance, the numbers line up to produce a tiny, positive cosmological constant like the one we measure. And in those rare, quiet universes, structure can form and life can arise. We find ourselves in such a universe not because it is likely, but because it is the only kind of universe we could possibly observe. This is the anthropic explanation taken to its ultimate conclusion. Our existence acts as a filter, selecting our specific cosmic address from a sprawling metropolis of dead ends. The idea is as philosophically unsettling as it is scientifically provocative. For some, it feels like a surrender, an admission that we cannot explain the most fundamental numbers in nature through pure, predictive theory. It swaps a puzzle of physics for a statistical inevitability in an unobservable ensemble. For others, it is a breathtaking expansion of reality, a logical outcome of our best mathematical frameworks. The debate cuts to the core of the scientific method itself. Can a theory that predicts everything, and therefore predicts nothing specific about our world, still be considered science? If the multiverse is real, but its other branches are forever causally disconnected from us, how could we ever test it? Some researchers look for faint imprints in our cosmic microwave background, scars from ancient collisions with other bubble universes in the primordial foam. Others seek deeper mathematical structures within string theory that might favor certain vacuum energies over others, making our universe less of a random accident. For now, the multiverse remains a powerful speculative escape from the fine-tuning nightmare, a canvas on which the strange luck of our existence might finally make sense. It suggests that the haunting perfection of our dark energy could be the signature of a reality far vaster and stranger than we ever dreamed. The multiverse offers a cosmic escape from fine-tuning, but some physicists seek the answer in a rewrite of our most fundamental law. What if gravity itself is an illusion, a side effect of something deeper? This is the startling premise of emergent gravity, a theory pioneered by physicist Eric Verland. He proposes that gravity is not a fundamental force woven into spacetime, as Einstein taught us. Instead, it emerges from the quantum entanglement of microscopic bits of information, like the pixels on a cosmic screen. In this view, space and the force of gravity are like the temperature of a gas, a large-scale property that arises from the collective behavior of countless underlying parts you cannot see. The most radical consequence of this idea is its explanation for dark matter. Verland's equations suggest that in regions of very low acceleration, like the outer rims of galaxies where stars orbit too fast, this emergent gravity naturally produces an extra gravitational pull. The effect perfectly mimics the presence of an invisible halo of dark matter, but without requiring a single new particle. The dark matter phenomenon, in this framework, is not stuff, but a signature of gravity behaving differently when the cosmic quantum information landscape changes. It is a breathtakingly elegant unification, turning two profound mysteries into one, yet, like all radical ideas, it faces immense challenges. The theory is still in its infancy, struggling to make precise, testable predictions that differ from standard dark matter models on all scales, especially for dramatic events like the bullet cluster collision. Other fringe ideas also tug at the edges of our understanding. Could gravity simply be weaker on enormous scales, as theories of massive gravity suggest, where the graviton particle has a tiny mass, or do we live on a four-dimensional membrane, a brain, floating in a higher dimensional space, with gravity leaking into the bulk and making it seem weaker, an idea from brain-world scenarios? These are not mainstream solutions, but they are vital. They represent the outer frontiers of human thought, where scientists are willing to question the bedrock assumptions of reality. They remind us that our current model, for all its predictive power, might be a magnificent approximation, a story that works until we peer into the darkness just a little deeper and find the plot is about to twist in ways we cannot yet conceive. This journey through 30 mysteries ends not with an answer, but with a question that echoes far beyond the cosmos. What does it truly mean that 95% of reality is completely unknown to us? This is not a failure of science, but its greatest and most humbling triumph. For all our brilliance, our telescopes, and our equations, we have mapped only the glittering shore of an ocean whose depths are still pure conjecture. The dark universe is a monumental lesson in cosmic humility. It is a clear, empirical statement that our most cherished models of physics, from Newton to Einstein, are stunningly incomplete. They describe the visible 5% with breathtaking accuracy, yet they are utterly silent on the nature of the overwhelming majority. This forces a profound shift in perspective. The universe is not merely stranger than we imagine, It is stranger than we can imagine, and the evidence for that strangeness is written in the very motion of every galaxy. This realization is the engine of the scientific method itself. It begins with a stubborn observation that refuses to fit, like stars orbiting too fast or supernova too faint. From that anomaly, a bold hypothesis is born, an invisible scaffold of dark matter, a repulsive energy in the vacuum. Then comes the relentless, global testing in mines deep underground, in colliders that recreate creation, and in telescopes that map the bent light of the unseen. The entire epic is a testament to the power of human curiosity and inference. We have deduced the existence of two dominant forces that govern the fate of everything, not because we saw them, but because we saw their shadow on the wall of our luminous cave. It proves we can reach beyond our senses to perceive the hidden architecture of reality. The dark universe, therefore, is not a wall, it is an invitation, a vast and silent frontier calling for the next generation of observers, thinkers, and dreamers to step into the unknown and shine a light. The story we have traced is a testament to human curiosity in the face of profound darkness. From Fritz Zwicky's first observation of missing mass to the ghostly halos revealed by Vera Rubin's rotation curves, we have followed the gravitational fingerprints of dark matter across the cosmos. We have seen it shape the cosmic web, bend light into mirages, and sail untouched through colossal collisions, yet for all its influence, its true identity remains a phantom, pursued in silent laboratories and particle colliders alike. Our journey then turned to an even more mysterious force, dark energy, discovered in the unexpected faintness of distant supernova. This repulsive pressure, woven into the vacuum of space itself, is now writing the final chapter of the universe, pulling the cosmos toward a cold, lonely, or perhaps even violent fate. We have confronted the staggering fine-tuning of the cosmological constant, wrestled with the Hubble tension, and considered the possibility that both dark forces might be connected in a single, deeper truth. Through 30 distinct mysteries, one overwhelming reality has come into focus. We have mapped the effects of a hidden world, but we have not yet seen its face. The fundamental nature of dark matter and dark energy remains the greatest unsolved puzzle in all of science, but this is not an ending, it is an intermission. We stand on the brink of a new era of discovery. The Vera C. Rubin Observatory will soon begin its decade-long scan, mapping the dark matter web in unprecedented detail. The Nancy Grace Roman Space Telescope will trace the expansion history of the universe with thousands of pristine supernovae. Together with Euclid, Daisy, and next-generation particle experiments, these instruments represent our most determined effort yet to illuminate the dark. The answers are out there, waiting in the bent light of distant galaxies and the quiet data of deep underground labs. Our epic journey through the dark universe proves that the most profound truths often begin with a single, stubborn anomaly. So stay curious, which of these 30 mysteries fascinates you the most? Is it the ghostly particles we cannot catch, the cosmic coincidence of our moment in time, or the ultimate fate written by dark energy? Let us know your thoughts in the comments below, and if you want to keep exploring the deepest wonders of the cosmos, be sure to subscribe for more journeys to the edge of understanding. The universe is 95% unknown, and the adventure to uncover it has only just